Okay, good afternoon. Let us start. So first two things, and after this class we'll have a fourth homework released. So as usual, the time for you to finish the fourth homework will be 16 days, right? 2 weeks plus 2 days. So I think it's pretty enough. And I'll suggest you to start the homework as early as possible, because please told me that when the deadline is approaching, many students come to the office hour. And if you can start earlier, then you can have more time, more resources about TA, about asking questions. The second thing is that I will be traveling on this Wednesday, so I cannot give lecture on Wednesday. So our TAs will have to wrap up this chapter, principal component analysis. After today's class, we're going to finish. We're going to finish this topic, namely the principal component analysis, and the TA will wrap up. And next week when I come back, we'll start with the next topic. So, okay, any questions?
So the homework due date is November 21st? 17 days.
I guess so. November 21st or November 22nd. I forgot. But when you first, yeah. When you download the homework from Canvas, you get it. So basically, it should be 16 days. Okay. So let us start the topic. So in the last lecture, we introduced a very important decomposition for general matrices called singular value decomposition. So singular value decomposition. And forgive my voice, because I recently got some cold. Don't worry, I won't. I guess I'm also good and won't infect any of you. So single value decomposition, most commonly used decomposition. So let us review what is single value decomposition. So for arbitrary matrix, the shape is n by d, meaning that it has n rows and d columns. So what's the form of the single value decomposition? Any idea?
A is equal to USV.
Yes. USV transpose.
Yeah.
So here's the general form for single value decomposition. That is, we can decompose arbitrary n by d matrix by the product of three matrices, U, S, and transpose of V. So here, U is an n by n orthogonal matrix, and V is a d by d orthogonal matrix, and S is kind of special. It is a n by d diagonal matrix. Right? So it sounds a little weird because when the n is not equal to d, how this diagonal matrix will look like. Right? So U and V are both orthogonal matrices, meaning U transpose U equals to U transpose equals to identity matrix. So this is a basic property of orthogonal matrix, and you can further verify that. That means the columns of U are orthogonal to each other. So what does it mean for two vectors being orthogonal to each other?
The inner product is 0.
Yes. That's kind of you should form a kind of instinct making connection of the two results, right? Orthogonal means so from a visualization, from a geometric point of view, orthogonal means they are perpendicular to each other, right? But from a computational perspective, it just means the inner product is 0. It's called orthogonal. And similarly, V is orthogonal matrix, meaning that V transpose V equals to V transpose equals to another identity matrix. Right? And similarly, the columns of V are also orthogonal to each other, meaning that their inner products are 0. Right? And we call columns U as left singular vectors. Left singular vectors. So columns of U called left singular vectors, and columns of V called right singular vectors. So this is just some definition. And then let us look at the matrix in the middle, S. We call it a diagonal matrix, right? So as the name suggests, diagonal means that elements in off diagonal
Is for the right singular vectors, is that V or V transpose?
V.
V.
Yeah, not V transpose. Yeah, not V transpose. And later we will explain why it is better to use V when we connect it to another important decomposition called Eigen Decomposition. That's for today's topic. So then let us look at the matrix in the middle, which is diagonal matrix, meaning that all diagonal elements are 0. Right? So what if n is not equal to d? Then what's the shape of S? So first we know S is an n by d matrix. Right? So let us simply assume n is bigger than d. Then S, the whole S will look like this, right? Like a refrigerator. So here is n, and here is d. And we see S is a diagonal matrix, means that we actually can cut the top d by d submatrix. Here's a top upper part of this matrix. We can construct a submatrix, right? And all the non-zero elements stay on the diagonal on this sub D by D matrix. That's where the non-zero elements of S lie in. And we denote those non-zero elements in S by sigma 1, sigma 2, until sigma R. So R is smaller than or equal to D. So, and also, we define that the order of those singular values that are sigma 1 is no less than sigma 2, no less than sigma 3, until no less than sigma R, and also the smallest non-zero element is bigger than 0. So basically, we assume this whole n by d matrix S contains R non-zero positive elements. And those non-zero positive elements stays on the diagonal of this matrix. And we assume they have been ordered according to their value. And then we call those R positive values as singular values. Singular values. And at the same time, you should be aware that R, namely the number of singular values, is exactly the rank of the matrix A. So again, the definition of rank. What is the definition of rank? What's the definition of rank? Anything?
It's a set of vectors with the size of the largest subset that is linearly independent.
Yeah, but you need to explain what is the set of vectors in the matrix A, right? Which are linearly independent. So basically, the set of vectors, as you mentioned, right, is actually can be the columns of A, or can be the rows of A. Doesn't matter. So we can prove that the maximum number of linearly independent vectors among all the columns in A is the same as that among the rows of A. So basically, rank of a matrix is just the maximum number of linearly independent columns, and also the maximum number of linearly independent rows. The two numbers are exactly the same. We can prove that. This is actually the basic conclusion in the linear algebra class. If you feel confusing about this concept, you can go back and look at the linear algebra textbook. So you can imagine when n is bigger than d, the locations of those singular values, right? So then we can consider when n is smaller than d, what will be the shape of S, and where do the singular values stay. So actually we can do it together, right? So this is n, this is d, right? So this is a shape of S, n by d. But again, we mentioned that when n is smaller than d, S is still a diagonal matrix. It just means that we can pick up first n columns to form a submatrix, and the singular values can only stay on the diagonal of the submatrix, right? And the remaining columns are set to 0. And similarly, in this case, where n is bigger than d, the bottom columns, bottom rows are just 0. So this is basically this is a singular value decomposition, and you should know what are the left singular vectors, what are right singular vectors, and where are the singular values. And according to singular value decomposition, we can use it to construct the best rank K approximation, as we explained in the last lecture, right? So what is the best rank K approximation? So given the original n by d matrix A, right? So I want to find a low rank matrix, but with the same size of A. So basically, we can denote this low rank matrix by A to the K. And it has the same size, n by d. But the rank, while we restrict the rank of a K is just K. And then among those all possible n by d matrices with rank only K, we want to find the one which has the smallest norm between 8 and the original matrix. So we want to find out AK which has the smallest norm. So here norms, we consider both the Frobenius norm and the 2 norm. So the question is, can we find out such a rank K n by d matrix which is as close to the original matrix A as possible in terms of the Frobenius norm and the 2 norm? And the answer is yes. And finding out this AK is extremely simple if you know the SVD decomposition. Right? So the idea is very simple. We just truncate. We just first solve the SVD decomposition for A, right? And we just truncate the singular values in S to K singular values. So this is the original singular value, singular values, right? This is the original S. And then to find out AK, we can fix U and V here. And then we just pick up the first K singular values, and then set the remaining elements in this diagonal to be 0. And we denote this truncated diagonal matrix by SK. Then our AK is simply U times SK times V transpose. That's it. And it's amazing that this AK can both minimize the difference, the Frobenius norm of difference and the 2 norm of difference. And this actually can be proved by a theorem called Actor-Young theorem. And it's kind of a tedious theorem, but it's not hard to learn that proof. And it simultaneously minimizes norm of the difference, the 2 norms of difference. And if you look at the theorem, it will also give you what's the exact value of the norm, of the minimum norm. And of course, when you truncate S by preserving only the top K single value, part of the columns in S will be 0, right? And then you can, to save computation, you can cut the corresponding rows in U and corresponding columns. You can cut the corresponding columns in U and the corresponding rows in V transpose to further save the computation. That's simply the rule to perform matrix multiplication. Just keep in mind. But the key idea is to remove some single values to find out the best rank K approximation. So any questions so far? It's just some jump start. So in the future of your applications on machine learning and data science, you're unnecessary to know how to prove that AK is the optimal, but
So you're truncating the smallest singular values, right?
yes.
Okay.
You cannot truncate the largest. If you truncate the largest, then this is not smallest. This is not smallest.
Can the smallest singular value be 0?
Of course.
Okay.
So if you
But
choose
everything
k,
has to be greater.
like if you choose k bigger than r, what will happen? What will happen if you choose k bigger than r?
Base k values.
Then the values you truncated are all zeros. That means you actually does not do any change to s. Then your ak is exactly a, right? The norm is just 0. Norm of the difference is just 0. That's reasonable because if you choose r, remember r is a rank of matrix A, right? If you choose k is bigger than r, meaning that you choose a higher rank matrix to approximate the original matrix which has a lower rank, then which matrix should you choose? You just choose the original matrix because its rank is not high. Any questions so far? Okay, so let's continue. So today we're gonna introduce another very extremely important, very widely used decomposition form. It's called Eigen Decomposition. So maybe I suppose every one of you has learned Eigen Decomposition in your linear algebra class. So today's discussion is mainly kind of review. It's kind of review. So the major difference between the Eigen Decomposition and the single value decomposition is that single value decomposition applies to arbitrary shift matrices, applies to real value and complex value matrices, but single value decomposition only applies to square matrix. And also not all square matrices have Eigen decomposition. In other words, although in practical applications, most people will ignore the precondition that you can apply Eigen decomposition. Precondition is that your square matrix must be diagonalizable. So this is all the basic concepts from linear algebra. So later we'll give the review. So Eigen decomposition. So to introduce Eigen decomposition, we should be clear about the concept of eigenvectors and eigenvalue. So eigenvectors and eigenvalues. So again, eigenvectors and eigenvalues are only computed for our square matrices. So now let us assume the matrix we want to focus on is the square matrix B, which is an n by n square matrix. So then what is eigenvector and eigenvalue? So as the name suggests, the eigenvector must be a vector, right? So we can denote it by V. And eigenvalue is a scalar, so we can denote it by lambda. And then we call V and lambda a pair of eigenvector and eigenvalue if this equation satisfied. That is B times V transpose, B times V equals to lambda times V. So here, B is n by n. So eigenvector must be n by 1. Right? N by 1 column vector. So the result will be another vector n by 1. And V here, n by 1 again, and multiply with the scalar is still n by 1 vector. Right? So if this equation holds, then the corresponding V and lambda are called a pair of eigenvector and eigenvalue for the matrix B. So the question is that eigenvector and eigenvalue are not unique. You can imagine, even for a specific lambda eigenvalue, how many eigenvectors do you have if there exists one eigenvector? idea? Oh, here we must assume V is not 0. 0 vector is not called eigenvector. So now if I know a pair of lambda V which satisfy this equation, so we can call V an eigenvector and lambda eigenvalue, can I find out other eigenvectors for the same eigenvalue lambda? Anything?
Yeah.
No? Any?
So given your lambda and your vector, if your vector is half the magnitude of another one, you can just double the lambda, and it would be the same.
Yeah.
It would be the same.
Your point is close. Your point is close, right? So you can imagine, even I fix lambda, when I multiply both sides by a scalar, a non-zero scalar, this equation still holds, right? So if there is a pair of V and lambda such that this equation holds, then I multiply V by 3. This equation holds as well. Multiply by 0.3, equation holds as well. So you can imagine, even for a specific lambda, you can have an infinite number of eigenvectors, right? So therefore, to make it convenient, we usually choose a specific eigenvector, which is a unit vector. We usually choose the eigenvector to be normalized, called unit vector. But it should be clear that actually eigenvector could be many. And we choose a unit vector for simplicity, for convenience. And one may ask, can we have some more intuitive explanation for the definition for eigenvector or eigenvalue? So we can try to do that because using a abstractive formula is a bad way to memorize those concepts. Right? So let us try to analyze what is the property of eigenvector, what eigenvector tells us. Right? So you can imagine in this n-dimensional space for an arbitrary vector. So let us denote by U. Suppose this is U. And now if we multiply our matrix B with U, what's the result?
Another vector.
Yeah, another vector. Right? This is n by n, that's n by 1, so the result is another n by 1 vector. Right? You can imagine here is B times U. Right? And among all possible vectors in the n-dimensional space, which kind of vectors we can call them as eigenvectors? We can associate the direction and position of the resulting vectors according to this equation. Right? So according to this equation, the definition of eigenvectors, we require that if for some vector B, that can be called an eigenvector, we require that what's the direction of B multiplying?
The same.
Yeah, the same direction of B, right? So this directly comes from the definition here, right? We require that the direction of B times B to be consistent with the original vector B, right? Of course, if lambda is less than 0, then BV could be in a totally opposite direction. But it must consistent. Right? It cannot have some angle between them, or an angle either be 0 or pi. Right? So this is a property of eigenvector. So you can imagine what is an eigenvector for a matrix. That is, when I multiply the matrix with the eigenvector, actually does not change the direction of the vector. This is called eigenvector. It only changes the length of the length of eigenvector. The fraction to change is encoded by the eigenvalue lambda. So this is a way to memorize the definition for eigenvector and eigenvalue. And also keep in mind, such vectors are not unique in the input space. I mean, unique does not mean, okay, if I scale v by some scalar, it doesn't mean. That means there could be also other directions, such that when v multiply this direction, it maintains the same direction. That means you can have multiple distinct eigenvectors with totally different directions. Those eigenvectors form the eigen decomposition, as we'll explain later. So any questions so far? Okay, great. So given conditions B, let us first imagine a little bit how to obtain the corresponding eigenvector and eigenvalue. Right? So one way is to solve this equation directly. So to solve this equation, we can use I guess that should be the first chapter's knowledge in linear algebra. So let us just do a brief review. So we can just move lambda v to the left-hand side and take v outside. It will be v minus lambda times identity matrix, then times v to be 0. So this is so solving the eigenvector and eigenvalue problems is equivalent to solve this linear equations. Right? So from analysis of these properties of linear equation, you can know the properties of the solutions. That means you could have a multiple lambda, and even for fixed lambda, you could have a multiple v to satisfy this equation. But here we're gonna skip this part because this is these are the detailed linear algebra knowledge. So if you are interested, you can go back, look into your linear algebra book. And yeah. So next, we want to associate the definition of eigenvector and eigenvalue to the singular value decomposition, as we focused in the previous lecture. Right? So let us try to say whether we can map eigenvectors, eigenvalues to the matrices of the singular value decomposition result. So again, this is singular value decomposition, which is n by d. So it is not necessary to be a square matrix. So the singular value decomposition is U as V transpose. So again, U is n by n, and V is d by d, and S is n by d. So we can take a look, and let us try to construct a square matrix. We can construct a square matrix in two ways. First, we can multiply A with A transpose. Now, what's the size of A transpose? What's the size of A transpose?
N by n.
N by n, right? So this is n by n square matrix. So it must have eigenvectors and eigenvalues. And another way is to multiply A transpose with A. So what's the size of A transpose with A?
D by d.
It's d by d, right? So now, using eigen decomposition, let us look at what can we get for their eigenvectors and eigenvalues. So we can start with A transpose A. So what is A transpose A? We can substitute A for its eigen decomposition, right? So then A transpose is what? what's A transpose? If we substitute A with its its singular value decomposition, what's A transpose?
Would it be U transpose S transpose V?
We need to switch the order. Because if you multiply multiple matrices and then take transpose, is equal to transpose all the matrices and multiply them in the reverse order.
So V S transpose U transpose?
Yes, yes. Yeah, that's the basic. That's basic rule. And should be familiar with. So A transpose would be B S transpose U transpose, right? And then can I see it? Can I see it? I can write it down here. So this is Eigen Decomposition. Okay. So let us look into A transpose A. Right? If we substitute A with is SVD decomposition, A transpose would be D S transpose, U transpose. And then we multiply A. Right? Then we just replace A with USV transpose. USV transpose. Now let us observe that. First, what is U transpose U?
Identity.
Identity, right? Because U is an orthogonal matrix. So that means you can just remove U transpose. So now end up with V S transpose. S transpose S V transpose. Now, if we multiply both sides by V, what can we get? What can we get? What if we multiply both sides by V on the right hand side, right? On the right, A transpose A times V, and this part multiplied with V. What can we get?
V transpose and V is just the identity.
Yes, because V is an orthogonal matrix as well. Right? We emphasize that. So that means we can just remove this V transpose V because it is identity matrix, right? And now we can take a look at this equation and see what can we observe, right? So again, V can be treated as a set of singular vectors, right? Orthogonal singular vectors. So we can write it as V1, V2 until Vd. And remember, V is D by D matrix. So each column in V is called a right singular vector, and those columns are orthogonal to each other. So now, if we multiply A transpose A with V, it actually to multiply A transpose A with each of the column. So if we write it as a list of those right singular vectors. So A transpose A multiplying V is A transpose A multiplying those vectors, right? And similarly, here, we can replace V by V1 transpose, V2 transpose, to VD transpose, and then multiply S transpose S. Now, if we use a block matrix multiplication, what's the result on the left-hand side? You can imagine each column is an element, right? So now if we multiply A transpose A with each column, what will be the result? An idea using matrix multiplication. So how can we represent the left-hand side? So we can simply multiply A transpose A with each of the column, right? That's the result. So my A transpose A with each column is a new vector, right? So actually the result can still be written as a column-wise form, right? So each column will be A transpose A times V1, right? The first column. The second column is A transpose A is V2. And we can continue until the last column is A transpose A is VD. That's the block matrix multiplication, right? So you can imagine, you can check for that according to the shapes. Right? A transpose A is D by D. Each column in V is D by 1. So you multiply A transpose A with each column, will end up with another D by 1 vector, right? It forms the columns in the result matrix, right? So each column will be A transpose A V1, A transpose A V2, continue, A transpose A VD. Any question at this point? It's just a matrix multiplication. So now let us look at this part, the right-hand side part. Right? So we should first look at what is S transpose S. So what is S transpose S?
The diagonal square matrix.
Yeah, diagonal square matrix. And what's the element of the square? In the diagonal.
The square of the singular values.
Yes, right. You can verify this, right? So let us still assume n is bigger than d, right? And the case for the n is smaller than d is the same, right? So if n is bigger than d, as we draw it numerous times, this is S, right? So you can imagine the singular values are stayed on the diagonal of the top d by d submatrix, and the bottom rows are just 0. And you multiply S transpose S. So we can imagine what is the shape of S transpose. So S transpose would be what?
D by N.
Yeah, D by N matrix. So you can just put your refrigerator down on the floor, right? So it looks like this. And the singular value will stay here. This is a sub D by D matrix. And this part is 0. And again, if you multiply these two matrices according to the block matrix multiplication, you actually what you can actually do? You multiply these two matrices according to the blocks. What can you do?
You can just remove the zeros.
Yeah, the result is remove 0. But I just want to refresh your mind, right? About those linear algebra rules, right? You can when you split the matrices into blocks, you can just treat those blocks as normal elements, right? And then you can treat, okay, this is actually two vectors, inner product between two vectors. Right? Just the difference is only that the element in those vectors are matrices. But the rule follows exactly the same thing, right? So if you consider the block matrices here as a two-element vector, right? This is actually an inner product, right? An inner product between the two vectors is simply the production between this element with this element. Right? They are corresponding production of two diagonal matrices, and this element with this element. What's the production between this element and this element? Simply 0, right? And what the production between this and this? It's just a simple square matrices, and each element is what?
Square.
Yeah, when you multiply two square matrices together, you are just multiplying their diagonal elements, right? You're just multiplying their diagonal elements. You can check for that. So here is sigma 1, sigma 2 to sigma r, and here is also sigma 1, sigma 2 to sigma r. And here 0 by 0 is just 0. The asm doesn't affect any result, right? So the result is simply the multiplication between this d by d submatrix and this d by d submatrix, they are the same. And so the result will be a sigma 1 square, sigma 2 square, until sigma r square. And those square of the singular values all stay on the diagonal. So that means S transpose S is a D by D square matrix, right? And each non-zero elements which stay in the diagonal of this square matrix is a square of the singular value. And so I can just draw it here. So sigma 1 square, sigma 2 square, until sigma r square. If r is smaller than d, then the remaining parts in this diagonal are simply 0. Right? So now let us consider if I multiply V with this square matrix, what's the result? What's the result?
Is it V1 times sigma 1, V2 times sigma 2?
Yes, exactly. Right? So again, if we use a block partition, here we partition the matrices into columns, right? And you can imagine this is just the row vector, but each element in this vector is another vector. Right? Then you multiply a row vector with a diagonal matrix. What's the result? Another row vector. Right? So here, that will be the first column vector in the result will be sigma 1 squared times V1. Right? The second is sigma 2 squared V2. And you can continue until the last term, the last vector is sigma d squared d, because it has d columns. But again, if r is bigger, r is smaller than d, then sigma d square must be 0. Any question at this point? Any questions?
So each sigma is a scalar, right?
Yeah, each sigma is good.
So each element in that is so each sigma times v is a column vector?
Yeah, the column vector. Yeah, you can imagine. Actually, this V is actually D by D matrix, right? I just partition them into columns. So V1, V2 to Vd are D columns. But you can simply treat it, because these are block matrices, right? You can simply treat it as a vector. But each element in this vector is a column. But even if you use a symbol V1, V2, Vd to represent them, you can still apply the matrix multiplication rule. That's called block matrix multiplication. Right? The rule doesn't change as long as the shapes between those elements are consistent. And now, if you multiply it with this diagonal matrix, you end up with this. You can verify it after class. It's just some matrix multiplication, and I can share with you some trick. You can memorize that so that you won't feel difficult to work out the result. So whenever you multiply a matrix with a diagonal matrix on the y-hand side, remember here, the position of the diagonal matrix you multiply to really matters. If you multiply matrix with a diagonal matrix on the y-hand side, the result matrix actually equals to multiply each row, each column with one diagonal element. So next time, whenever you multiply a matrix with a diagonal matrix on the right-hand side, remember this rule. Do not need to do the matrix multiplication again. You just memorize it. You just multiply each column of the matrices by one diagonal element. But if you multiply your matrix with the diagonal matrix on the left-hand side, things going to change. It is equal to multiply each row of the matrix with a diagonal element. just to memorize this simple trick. Then next time we will do the matrix multiplication. You won't need to follow exactly, just write down the result. And you can verify it. You are verified after class. Very useful trick. So any questions so far? Okay, great. So now we can write that. We now derive the left-hand side and right-hand sides, both in terms of columns. Those are two matrices, right? So when they are equal, means that their columns are equal. That means for both sides, the jth column will be what? For the left-hand side, the jth column is A transpose A times Vg, right? And what about the jth column on the right-hand side? What is jth column on the right-hand side?
Sigma j squared times Vj.
Yes, yes. We just derive the column-wise result, right? So in the right-hand side matrix, the jth column is simply sigma j squared Vg. That is the square of the singular value, j singular value of A times g's right singular vector. So now from here, what can we observe?
Sigma j squared is an eigenvalue for the eigenvector Vj for the transformation A transpose A.
Yes, exactly, right? So that's from the definition here, right? So for an arbitrary square matrix, if there is a vector v and lambda which satisfy this equation, that means v and lambda are a set of a pair of eigenvector and eigenvalue. Right? Here, for each singular vector vg and the corresponding square of the singular value, this equation holds, right? That means vg and and sigma g squared is a pair of eigenvector and eigenvalue for A transpose A. And then the next question will be how many such pairs of eigenvectors and eigenvalues do we have for A transpose A?
K. K.
Okay.
J.
J is some arbitrary index I can choose. So you can count the columns here, right? So how many columns do we have?
D.
Yeah, D, right? Because V, the right singular vectors are in total D, right? We have a D by D orthogonal matrix V, where each column is a right singular vector. That means we have D columns in V. And for each column of V, we have a corresponding singular value. Of course, if J is bigger than R, then sigma G squared is simply 0. Then we form a pair of eigenvector and eigenvalue. So in total, from the SVD, we can get D singular, D eigenvectors and eigenvalue pairs for A transpose A. Any questions? Any questions so far?
We will talk about A transpose.
Yeah, that's we're gonna talk about right now. Any questions so far? This is the first important observation, right? So when we have the singular value decomposition for arbitrary matrix A, we first observe that the square of singular values and also the right singular vectors form eigenvector and eigenvalues for A transpose A. And similarly, we can look into A transpose. So what can we observe from A transpose? We can guess that must relate to the left singular vectors U, right? And indeed it's true. So when we substitute A for, replace A with its Eigen Decomposition, we can find out this is a U as V transpose times A transpose is V as transpose U transpose, right? And now V transpose V is what? Identity matrix, right? Remember, U and V are always orthogonal matrices. So V transpose V will be identity matrix, so we can remove it. So finally, we'll end up with U SS transpose U transpose. Similar form. Now, if we multiply both sides by U, we get A transpose equals to U times SS transpose, right? Because when you multiply U on the right-hand side, U transpose U is an identity matrix again, right? You can remove it. And now it's this. So now what can we observe?
Do you mean A times A transpose times U?
Oh, sorry. Yeah. Times U. So now what can we observe right now? We can do the same analysis here, right? So A transpose A times B is equal to something like this, right? So similarly, A transpose times U equals to A transpose U1, A transpose U2, A transpose UN, right? Because U is n by n matrix, so it has n columns which are orthogonal to each other. Okay? And similarly, we can take a look at the size of SS transpose. So S is n by D, so SS transpose is n by n again, right? But when you do the SS transpose, so here is SS transpose. So here is S, here is S. So here is the positions for singular values. And if you multiply with S transpose here, we just switch the order here. Right? So here's S transpose. Then when you multiply these two matrices, what's the result?
N by N square matrix.
Yeah, n by n square matrix, right? And using a block matrix multiplication again, right? So you can imagine this is a vector. This is a vector. This is an auto product of two vectors. So you can imagine, okay, in this result, n by n square matrix, which is SS transpose. The first d by d part is just this part times this part. And then what is the remaining part? Simply 0, right? Because you can imagine, right? This is a block matrix. So this part, this submatrix, is the first submatrix multiplication. So their diagonal is the square of the singular values. But for this part, right, using the auto product, right? So this part will be this diagonal matrix multiplied 0. Right? So this is 0. And this part will be the bottom part here multiply this 0. And the last part is 0 multiplied with 0. Right? So we can check the consistency according to the shapes. Remember, if you are doing block matrix multiplication, as long as your partition are consistent in terms of matrix shapes, you can follow the same matrix multiplication rule. So now we can say actually S transpose is n by n diagonal matrix, and the first R diagonal elements are the square of the singular values. Right? So the remaining part are simply 0. So now when we multiply SS transpose with U here, we end up with a similar result. Right? So the first column will be sigma 1 squared times U1. Right? Second will be sigma 2 squared times U2, and continue until sigma n squared times UN. Right? So here, of course, sigma n squared will be 0, right? If R is smaller than n. So from this, what can we observe? What can we observe from this equation?
You get the same eigenpair relationship, but with n eigenpairs.
Yeah, of course, right? We can because these two matrices are the same, so each pairs of columns are the same, right? So the jth column here is A transpose uj, right? And jth column on the right hand side is a sigma j square uj. According to the definition of eigenvector and eigenvalue, it means what? Uj and the square of singular values, sigma j squared, right, is a pair of eigenvector and eigenvalue for A transpose. Now, what can we observe? From singular value decomposition, we find that the pairs of the left singular vectors and the square of singular values form the eigenvectors and eigenvalue pairs for A transpose. And the pairs of right singular vectors and the square of singular values form the eigenvector and eigenvalue pairs for A transpose. That's very amazing result. And also, you will see that actually the square of the singular values are shared eigenvalues for both A transpose A and A transpose. And that's a very interesting observation, and also a very famous connection between the singular value decomposition and eigenvector eigenvalues. Any questions so far?
So no matter if you decompose on A transpose A or A transpose, you get the same eigenpairs either way.
As I just mentioned, well, eigenvectors, eigenvalues are not unique. But I can tell you that many implementation of eigenvectors and eigenvalues for those this is called A transpose A and A transpose called Hermitian matrix. They are implemented through singular value decomposition. And if they are implemented through singular value decomposition, then they will result the same set of eigenvectors and eigenvalues. But if you use other methods, there's no guarantee. Because any eigenvector, any pairs of values and vectors, as long as they satisfy this equation, they are eigenvector and eigenvalues. But from eigenvalue, from the singular value decomposition, you can find out their relationship. Any other questions? Okay, great. So after the discussion between the projection of eigenvector, eigenvalues, and the singular value decomposition, we now introduce the Eigen decomposition. So what's the Eigen decomposition? Suppose a n by n matrix B is diagonalizable. Then we'll have n linearly independent eigenvectors. So V1, V2, Vn. And we can denote the diagonal matrix where each element are one corresponding eigenvalue by L. So here's the diagonal matrix L. Then we can represent B as B, L, B inverse. So this is called Eigen decomposition. So first, the matrix must be a square matrix. And second, the matrix must be diagonalizable. And then we can find out n linearly independent eigenvectors to form a matrix V. And now that these eigenvectors are linearly independent, it means that V is invertible. So because the rank of V is n, right? So V must be invertible. And also the corresponding eigenvalues, we can form it as a diagonal matrix, L. Then we can represent B as V times L times V inverse. So this is definition for eigen decomposition. And again, it is just a re-representation of a square matrix. But here, you should be aware that B must be diagonalizable. This is actually something you have met in your linear algebra course. So here, I just review it. So what is diagonalizable? Meaning that you have a full rank matrix P that you multiply P inverse with B times P is a diagonal matrix. Then B is called diagonalizable. So basically, that means if there exists an invertible matrix P, such that P inverse times B times P is diagonal, this is called diagonalizable. So only when B is diagonalizable, it has eigen decomposition. If it is not, then there is no eigen decomposition. You only have eigenvectors and eigenvalues. So of course, when B is diagonalizable, then P could be what? Yeah, V, right? Because according to its eigen decomposition, you multiply B by V inverse B and V, you end up with L, right? So P is simply a V. So this is an eigen decomposition. But the most commonly used eigen decomposition is when B has has an important property. That is when B is a symmetric real matrix. So be aware that eigenvector and eigenvalue could be complex values, although B is real. But it is possible that V and lambda could be complex values. But if B is a symmetric real value matrix, first is B is symmetric, second B is a real value, then we can always find out a set of orthogonal eigenvectors, meaning that those eigenvectors are orthogonal to each other. And if we normalize each eigenvector, we end up with a orthogonal matrix B. And then the eigen decomposition of B is simply V transpose. But this is for symmetric real matrix. So why? Because V is orthogonal, right? So we know V transpose is identity matrix. So actually V transpose is what?
Inverse.
Yeah, V inverse, right? So what's the definition of inverse matrix? If you multiply a matrix, C is identity matrix, right? So W is called inverse of V. Right? So here, V transpose is the inverse of V. So our eigen decomposition now becomes V transpose. So what's the benefit of this form? What's the benefit of this form? This form can be further expanded to represent B as a summation of outer product of eigenvectors. You can compute it. So because now we do not need to invert V, right? We do not need to invert V in the original definition of eigendecomposition. We just use V transpose here. So now you can try to multiply V1, V2, Vn times lambda 1 to lambda n, and then times V1 transpose, V2 transpose to to Vn transpose. And if you do this multiplication, you will find that this can be written as the summation 1 to n, and each summand is simply the eigenvalue multiplied with the outer product of the corresponding eigenvector, which is Vi times Vi transpose. So now we can write down our matrix B as a summation of the outer product for the eigenvectors. So that's a major benefit of Eigen decomposition form for a real symmetric matrix. So any questions so far?
It's the inner product of V and its transpose.
Not inner product. Vi times Vi transpose. So it's actually outer product, not inner product. You can imagine this is n by 1, right? This is 1 by n. So the result will be n by n matrix. So this is called outer product. Any other questions? Okay. So this is a commonly used Eigen decomposition form for real symmetric matrix. And in your future exploration in data science or machine learning with real paper, you'll find many papers because their matrix is symmetric, and they directly replace this matrix with a summation of this outer product for eigenvectors. So don't feel strange. That's that assumed as common sense. Okay. So and also another commonly used symmetric matrix is called a positive definite symmetric matrix. It's called positive definite matrix. So what is positive definite matrix? It is, the definition is simply requires that the eigenvalue, each eigenvalue of this matrix is strictly positive. Then it's called a positive definite matrix. And also you may have learned in your linear algebra course that positive definite matrix must satisfy a property that for arbitrary non-zero vector x, the quadratic form x transpose B x must be strictly positive. Right? This is actually another definition for positive definite matrix. That is for arbitrary vector, the quadratic form, that is x transpose times B times x must be positive. So actually, these two definitions are equivalent. How do you verify that? You can try to multiply. You can try to replace B with its Eigen decomposition form. You will find that when each lambda I is strictly positive, this result is always positive, and then leave it as your practice. And similarly, we can define semi-positive definite matrix. So what is semi-positive definite matrix? It simply requires each eigenvalue to be no less than 0. So it could be 0. Then it's called but it cannot be negative. Then it's called positive semi-definite matrix. So those positive definite matrix and positive semi-definite matrix are very widely used. For example, if you build up a multivariate Gaussian distribution, the covariance matrix must be positive semi-definite. And of course, if there is some eigenvalue to be 0, then it's called tweaked Gaussian distribution, and there's some explanation on that. But at least it requires the matrix is a positive semi-definite, and also like kernel learning. Your future, if you take some class in machine learning, you learn some kernel learning. You will construct a kernel matrix, and the basic property that requires a valid kernel is that any matrix constructed by kernel must be positive semi-definite. So in the last 5 minutes, I want to explain a general method to compute eigenvector and eigenvalue. And it's extremely simple. It's called power method. So the power method will guarantee to return you the eigenvector and the corresponding and the largest eigenvalue. So if I want to compute the largest eigenvalue and the corresponding eigenvector for the matrix B, and with q iterations, so here's the procedure for power method. So we first get an initialization. Initialize u0 as a random unit vector. And then how do we update the u? We just repeatedly multiply the current vector with u. That's it. So ui will be b times u I minus 1. And then, of course, we need to renormalize because we assume our vector, result vector is a normalized vector, unit vector. So we can renormalize it by divided by the Euclidean norm. And then we are repeatedly doing this until the maximum number of iterations, and finally we return the current vector. Then it can guarantee this result is as close as possible to the eigenvector which corresponds to the largest eigenvalue. This is called power method. And I suppose when you look at this procedure, you are able to implement the power method, right? Very simple. You just start with a random unit vector, and you repeatedly multiply this vector with our matrix V. And it can guarantee you that finally, if you have sufficient large number of Q, you end up with the eigenvector which corresponds to the largest eigenvalue. And as your this is your obligatory practice. Why it's called obligatory? Because you will need to finish the homework form. So I request everyone to read the explanation about why our method can return an eigenvector. That is on the course material. And in the homework form, there will be a hint and ask you to read that material because I don't want to cover it. It's just some kind of derivation. But when you read out this derivation, you will have a sense why it can return you the eigenvector which corresponds to the largest eigenvector. So anyone have questions regarding the procedure for power iteration?
Instead of setting the number of iteration, can we just check if the u doesn't change the unit vector?
I guess not.
No.
Yeah, because actually this is kind of you can imagine this kind of fluctuation method, and finally it will end up with 0. So it's not very reliable to detect relative changes. Of course, you can when you set up the tolerance level to be very, very small, it is possible. But most commonly used methods to set up some maximum number of iterations. And also, because it is so simple, there is some criticism on the number of iterations that are required to converge to the true eigenvector. So usually the Q should be as large as possible. But if you just want to get the result vector which is sufficiently close to the to some eigenvector, that's fine to set up Q to be reasonably small, like just 2 200 or 300. That's fine. Any other questions?
Well, so this will only this returns the eigenvector that corresponds to the largest eigenvalue.
Yeah.
So to construct alpha, we need n eigenvalue and eigenvector pairs, right?
Yeah.
So how do we get different eigenvalue and eigenvector pairs from the power method?
Yeah, that's a great question. Yeah, that's something I'm going to discuss in the last 1 minute. Right? So you can imagine, after running this power method for the matrix B, you end up with an eigenvector, and you can also calculate the largest eigenvalue. How can we calculate? Use the definition of the eigen decomposition, right? No, eigenvector. So we know for eigenvector, we have d times this eigenvector equals to lambda times the eigenvector, right? So now you can multiply both sides with u. That means you multiply the left-hand side by u transpose and u transpose. So actually you're doing inner product, right? Inner product on both sides with u. So now, this one is a scalar. It's a quadratic, right? This one, what is this one? It's a scalar, right? Because u is normalized. U is a unit vector. So u transpose times u is just 1. So actually, it ends up with the corresponding eigenvalue. So once you get eigenvector, you can simply compute the quadratic form. The eigenvector transpose times the matrix times the eigenvector. You end up with the corresponding eigenvalue. Any questions? You can simply verify. After the class. It's straightforward. It's straightforward. You just so according to the definition, right? Just multiply. You just do the inner product on both sides. You end up with this result. So the key question is that when you calculate the largest eigenvector, how can I obtain the next second largest eigenvector and continue, right? So the method here is to factor out this. How can we factor it out? We can use the Eigen Decomposition we just mentioned. So remember, we just derived that this is the Eigen Decomposition. Right? It's a summation of the outer product of the eigenvectors weighted by the eigenvalue. And now we just subtracted one outer product from our from the computation result we just obtained. Right? If we subtract b by, suppose we denote the largest eigenvalue as lambda 1 and the vector as v1, right? We just subtract both sides by lambda 1, v1, v1 transpose. So on the right-hand side, the summation does not contain the largest eigenvalue. It only contains the second largest eigenvalue. Okay? So these are the Eigen Decomposition for the left-hand side. And then, what should we do next?
Do the power method on also.
Yeah, we do the power method again. We do the power method on b minus lambda 1, v1, v1 transpose. And do it again. What can we get? The second largest eigenvalue, eigenvector, here, right, from here. And now we are subtracted again. And we replace the subtracted matrix into the power method. We run again. We get a third largest eigenvalue, eigenvector. We do it again and again until some point that eigenvalue we obtain is just 0. Then we stop, because there's no meaning to continue to do that, because the remaining eigenvalues are all 0. So any questions so far? Okay, so this is a basic idea, and in the Cosmic cube, it assumes that B has a structure that equals to A transpose A. If it looks like this, we can just, when we compute the power iteration, we can replace B with A transpose A. It will save some, further save some computation. So you can look into the cost material and say why. But the basic idea is like this. And also in the cost material, it says how to factor out the effect of your learned eigenvectors, eigenvalue is performed on A. But when you calculate the subtracted A and with its transpose to obtain B, you will find they are totally equivalent to subtract B directly with this eigenvector, eigenvalues. So I encourage you to try to verify it after the class. Okay? Okay, thanks. So I apologize again. So Wednesday I will not be here, and also the office hour on Thursday I'm not available again, but you can come to the office hour in the TA's room. And also you're welcome to email me any questions in Canvas or in email. Okay, see you on next month.